Okay, I hope all of you could see it. Okay, if there are more students to join, yeah, we will on the go. We will accept them. Okay, now we'll start it. So we have the chemical reactions is what we are going to discuss now. So we can give the heading chemical reactions of haloalkanes. Okay, so in our last class we were discussing mainly the preparation. So right now we will discuss the chemical reactions of haloalkanes, very important part. Okay, so from your idea, we know haloalkane is nothing but RX, correct? Alkyl halide, that is the other way of naming it, or we can say CH3Cl, one simple example. So here, what is the characteristic reaction? First point to be noted here. Characteristic reaction given by haloalkane, given by alkyl halide. We can say it like that also. Alkyl halide. Can anybody tell that answer? What is the characteristic reaction given by alkyl halide? I can give you one example. For example, if you have RX, okay, I am going to treat it with a nucleophile Nu minus. Then after the reaction, you will get RNu with the X minus. This is the most common reaction given by alkyl halide. So what is this reaction called? Can anybody tell? So the simplest way to understand this reaction is you can see like this. Here halogen was there. Okay. This halogen was substituted with whom? The nucleophile Nu. So since it is replaced with Nu, we can say it is a type of what reaction? Substitution reaction. It is a type of substitution reaction. Next question is, who is substituting that? Instead of X, who is coming here? A nucleophile is coming here. So I can say this is a type of nucleophilic substitution. You can say it's a type of nucleophilic substitution. So we can say the characteristic reaction of alkyl halide is nucleophilic substitution. It is also called SN reactions. It is also called SN reactions. So this is further classified into two. First one is called SN1 reactions and other one is called SN2 reactions. Okay. Now let's start analyzing what is SN1 and SN2. Okay. So we will first go with SN1 reactions. Okay. So here most important point to remember here is what is this 1 stands for? Here 1 stands for the order. So that means this is a reaction of order 1. Okay. So let me explain what is nucleophilic substitution SN1. So please understand both SN1 and SN2 are nucleophilic substitution, but one is of order 1 and other is order 2. So in SN1 reaction, what happened here is usually this is given by 3-degree alkyl halides. Okay, then it can be given by 2-degree alkyl halide, then only primary alkyl halide. So I can say the rate of reactivity, it is like this. Rate of reactivity will be like a 3-degree alkyl halide will be reacting very fast to give an SN1 reaction, then 2-degree, then primary. Primary will not give. Okay, but we can say last it will come. Now, what is the determining factor? Why you say 3-degree alkyl halide will give an SN1 reaction? So to understand that, I will explain its mechanism. Then you will understand. For example, I will take a 3-degree alkyl halide like CH3, CH3, and you have another CH3 here. So we know that this carbon is connected to, or we can see chlorine is connected to a carbon that is connected to 3 other carbon atoms. So that's why we say this is a 3-degree alkyl halide. Okay. Now this 3-degree alkyl halide, I am treating it with, for example, a strong nucleophile like OH minus. Okay. So here I am, this strong nucleophile is present in the form of water, H2O. So this will ionize in the medium as H plus and OH minus. Okay. Now this is one case. Now what will happen here during the reaction? In the first step, we can say here this carbon chlorine bond is a polar bond. Okay. Why it is called a polar bond? Because chlorine is highly electronegative in nature, and because of this electron will stay near to chlorine. And what will happen here? The bond will be like this here. Okay, I can say the bond over present near to chlorine is very thick, and near to carbon it becomes thin. Why? Because the electron pair is near to, I can say, near to chlorine. So this will be like this. Okay, so what will happen here is this bond becomes very weak, so you can easily break this bond. When this bond is broken, the electron pair will go with chlorine and it will be like Cl minus, and carbon will be carrying positive charge. Clear? So I can say first step of this reaction is chlorine being a very good leaving group. We know chlorine is a very good leaving group. So it will leave the compound and this will become CH3, CH3, and this will become CH3, and there will be plus charge here, and Cl minus will be moving out. And we can also say a reason why chlorine is a very good leaving group, because chlorine, it has its configuration 2, 8, 7. So chlorine need only one more electron to complete the octet. So when this electron of carbon goes to chlorine, its octet will become Cl minus will have a configuration 2, 8, 8. Its octet is complete. That is the reason chlorine is a very good leaving group. So tell me, what is the intermediate formed in this reaction? So you have chlorine left out. Here we can see carbon with a positive charge, and this is called carbocation. This is called a carbocation. So I can say the intermediate, okay, the intermediate in SN1 reaction, intermediate in SN1 reaction is what actually? It is a carbocation. Is this clear until now? Hello? Yes, ma'am. Okay, somebody is waiting. I'm accepting all. Okay. Okay. So I hope until now it is clear for everyone. Okay, so we got a carbocation as the intermediate. Now we know that this is a slow step. The formation of carbocation is a slow step. And this is the first step of the reaction. Okay, let me draw with a different color. So I can say this is the first step of the reaction. Okay. Now we have the second step. So in the second step, what we have, the starting thing is which one? You have the carbocation is present, correct? So I can draw the carbocation CH3, CH3, then you have the last CH3 and with the positive charge. Okay, now what will happen? We know that water, it's a weak nucleophile. How will you check whether a nucleophile is weak or not? Very simple. Suppose if they are giving like OH minus and H plus, if there is negative charge is present explicitly, then I can say it is a strong nucleophile. But suppose they are not giving like this, instead they are giving like water, H2O, then I can say oxygen has two lone pairs. So if it is present as a lone pair, then I can say it is a weak nucleophile. This is the way we will identify whether it is a strong nucleophile or a weak nucleophile. Okay. So I know here water is a weak nucleophile. So what it will do, it will slowly ionize us as H plus and OH minus. And now you can see this OH minus will come and attack this positive charge. And you will get what actually? CH3, CH3, and you have CH3 and you have OH. But you can think here OH minus is negative in nature, this is positive in nature. It is almost like a reaction between positive and negative. So we can say this is very fast, or it is almost like an ionic reaction. Okay, since it is very fast, we cannot measure its rate. So from these two reactions, the slowest one is this one. So we can measure its rate only. That's why it is called the rate determining step of the SN1 reaction. So the formation of carbocation is the rate determining step. So with this only we can measure the rate. So that's why when you write the rate of this equation, we can say rate is equal to rate constant into concentration of this only will come. Because when you are looking at this reaction, there is no water coming during this step. So we can say this is dependent only on the substrate concentration, that is the 3-degree alkyl halide. So since it is depending only on this one, we can say its order is 1. That's the reason why order 1 is coming here. Is this clear for everyone until now? Okay. Now we will see the stereochemistry of SN1 reaction. What do you mean by stereochemistry of SN1? We will see that. I can write it here like this. Stereochemistry of SN1 reaction. So to explain the stereochemistry, I will start from the step 2. Okay, so in step 2 we have seen there will be carbocation like CH3, CH3, and you have CH3 and there is positive charge. This is the second step starting. Now tell me what is the hybridization of this carbon. If I see here, this is S, this is P, and this is P. So I can say the hybridization of this carbocation is sp2. If somebody has sp2 hybridization, we know that its shape is planar. Okay. If you have sp hybridization, what is the shape? We know it is linear. If it is sp3, what is the hybridization? What is the shape? Tetragonal. We are learning this. Okay. So here sp2 means it is planar. What do you mean by planar? Planar means all the atoms are lying in one plane. To understand that, I will draw like this. So I will draw a horizontal plane like this. Okay. Here you can see carbon is there. CH3 is present here. Okay. Here another CH3 is present. Here another CH3. So all are lying in this plane and there is a positive charge like this. Now we know that in the second phase, the OH minus, which is the nucleophile, okay, this can come and attack this compound, correct? This can come and attack this compound either from the top like this, okay, or it can come via bottom and attack the carbon. So there are two possibilities. Suppose if it is coming and attacking from the top, suppose we will get something like this, CH3, okay, C, then you have CH3, then you have another CH3 and OH will be rising like this, OH from the top. Okay, suppose it is coming from the bottom. In that case, we will get a compound like this, CH3, here C, CH3, and there is another CH3 and you have OH like this. So here, suppose this compound is optically active, then I can say one that is coming from the top will be dextro, or one will be dextro and other will be levo, correct? Because one is from the top and other is from the bottom, so the rotation will be different in both cases. So we can say the stereochemistry of SN1 reaction is, after SN1 reaction, please remember this is a very important point, after SN1 reaction, what you will get, you can say 50% chance is there. It is coming from the top, 50% it can come from the top, 50% it can come from the bottom, equal probability. So I can say there is a possibility that 50% of the product, 50% of the product will be dextro, okay, and there can be 50% of the product will be what actually, tell me, levo. So such a type of mixture where you have equal amount of dextro and levo present as 50% is called racemic mixture, is called racemic mixture. So now I can say a simple conclusion, SN1 reaction result in optically active compounds. It result in what? The answer is racemic mixture. Racemic mixture. Is this understandable for everyone? Hello? Okay, I hope the stereochemistry is clear for you. Now let's go to the factors favoring SN1 reaction. The third important thing to be understood regarding SN1. So we can say factors favoring SN1 reaction. Okay, factors favoring SN1 reaction. So I can say if you have a weak nucleophile, then it will always favors SN1 reaction. Okay. The second one factor I can say, if you have a polar protic solvent is present, then this will favor SN1 reaction. Usually this will be helpful in 2-degree alkyl halide, because if you have a 3-degree alkyl halide, you don't want to look at these situations, whether it is weak nucleophile or polar protic solvent, you don't want to look at. You can easily say this will give SN1 reaction mainly, or E2. We will go to elimination second half. We will now discuss only on substitution reaction. So we can say it will easily give SN1. But if it is a 2-degree alkyl halide, then there is a two possibilities are there. So this can give either SN1 reaction or SN2 reaction. So students will get into a confusion. For example, if you are given a compound like this, CH3, CHCl, CH3, and I know that this is a 2-degree alkyl halide. Okay, so here students will ask me a doubt, sir, whether it will follow SN1 or SN2. This depends upon these two criteria. If you are using a weak nucleophile, how will you know whether it's a weak nucleophile? Check for example, if you are given CH3OH, tell me whether it's a strong nucleophile or a weak nucleophile. I know that oxygen has lone pair present like this, so I can say it is a weak nucleophile. Suppose the same compound they are giving it like this, CH3ONa. Then I know that here sodium is highly electropositive, oxygen is highly electronegative. So it will always present like CH3O minus and Na plus. Then I can say here CH3O minus is a strong nucleophile. Clear? This is how you need to understand. So if it is given like this, or even if it is water, H2O, then I can say it is a weak nucleophile. But if it is given with the electropositive element, for example, sometimes they will give like this, C2H5OK. Here O minus and K plus. So I can easily say this is a strong nucleophile. Okay. So if weak nucleophile is present, then I can say this will favor SN1 reaction. Okay. And the next important factor is if there is a polar protic solvent. So polar protic solvent means any solvent which is capable of donating a proton. That is called a polar protic solvent. For example, water. Water can donate H plus, so it's a polar protic solvent. Now CH3OH, methanol, this can donate H plus. So this is also a polar protic solvent. And anything. So there are polar aprotic solvent is also there. For example, acetone. Okay, these two are polar protic solvent. Suppose they are given acetone, CH3COCH3. I know that there is no H plus that can be donated. This hydrogen is not donatable because it is linked with the carbon, so it will undergo only free radical breaking. So there is no H plus to donate. So I can say this is a polar aprotic solvent. So if it is a polar aprotic solvent, it will favor only which one? SN2 reaction. And there is another one called dimethyl formamide. This is another very important polar aprotic solvent. Okay. So DMF I can written like dimethyl CH3. There is two CH3 is there, and there is a formamide. So there will be some NH2 group will also be there. So you can remember like DMF. Okay. So this is the best way to understand it. So if 2-degree alkyl halide is given, check for weak nucleophile, then SN1, and if there is polar protic solvent is also there, confirm that this will undergo SN1 reaction. Whether this is clear for everyone? The three possibilities we have discussed. Clear? All of you?
Yes, sir.
Okay, now let's see, somebody is there in the waiting room. Okay, every time we need to look this. Okay, nobody is there, it's fine. Okay, so now we will go to the second step, that is the SN2 reaction. We will go to SN2. So we can give the heading nucleophilic substitution of order 2, that is called SN2. Now coming to the SN2 reaction, the first thing you need to know is it happens in a single step. Okay, we have seen that the SN1 reaction was happening through 2 steps. This will happen in single step. Now the next thing we need to remember here is the order of reactivity. Here is 1-degree alkyl halide will give more, then 2-degree, and then 3-degree. So usually 3-degree alkyl halide will not give SN2 reaction. Okay, only 1-degree and 2-degree will give. Now what is the important thing, important factor that governs SN2? In SN1, what was the important factor? We can say the intermediate that is formed. If the intermediate formed is a stable one, here, if the intermediate formed is a stable one, then only it will go to the step 2. Otherwise, if the intermediate is not stable, then what will happen? This carbocation will die out in the reaction medium and there will be no second step. So we can say the main factor that govern an SN1 reaction is the stability of carbocation. Please remember, carbocation stability is the main factor that drive a particular reaction to undergo SN1 mechanism. Now, similarly, I can say that for SN2 reaction, the main factor or main driving factor is, please remember this point, main driving factor is which one? I can say that is steric hindrance. Steric hindrance. Please remember this. So that is the reason if I am taking a 3-degree alkyl halide, you can see here okay, so you can see here mainly there is another CH3 here, okay, and we can see here chlorine is present, but we can see 3 CH3 molecules are present here. So this is, if you expand it and draw, you can see here hydrogen, here hydrogen, here hydrogen, okay, here another carbon with carbon, here also hydrogen, here also hydrogen, here also hydrogen, and here another carbon with hydrogen, here hydrogen, and here hydrogen, and here chlorine is present. Now you can see here there is full of hydrogen atom and carbon here, so there is a lot of hindrance is there, correct? So there is a lot of hindrance you can see here. So that's the reason here SN2 mechanism will not happen. Rather, what will happen here? SN1 mechanism. So we need to say that in SN2 there should be less steric hindrance. Okay, main driving factor is less steric hindrance. If there is suppose if you are taking a 1-degree alkyl halide, we know that CH3Cl. So we can see here carbon with hydrogen, 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 and chlorine is present. So there is less steric hindrance here. So that's the reason why 1-degree alkyl halide will give SN2 mechanism. So let us explain how this SN2 mechanism happens. So then you will understand why the 3-degree alkyl halide is not undergoing SN2 mechanism. Okay. So after explanation, you will get a clear picture. Okay. So let's see the mechanism of SN2. Okay, so in SN2 mechanism, the most important thing to remember here is the nucleophile that is used here. Okay, the nucleophile should be strong. Nucleophile should be strong in nature. Okay, and what are the other factors that will be favoring SN2? I can say polar aprotic solvent. Polar aprotic solvent will favor SN2. Now let's see how that is happening. Mechanism. Okay, so let's draw the mechanism, then you will get a clear picture. So I can say if you have a 1-degree alkyl halide like this CH3Cl, and I know that in this reaction you are having a strong nucleophile, so something like C2H5 O minus and K plus. So I can say O minus is a strong nucleophile. It will not wait until this CCl bond breaks. Rather, what it will try to do, if you see here carbon, okay, with the chlorine is present, okay, and this chlorine has lone pair like this is present, correct, and you have hydrogen present like this. Okay, now what this nucleophile will try to do here is it will not come via friend way, because there is lot of lone pairs are present here, so this lone pair will repel the minus charge. So what it will try to do is it will come via the back side and attack the carbon atom. Okay, please remember it will come via the back side and attack the carbon atom. So I can show it like this. Please see that. So it will come via the back side and attack the carbon atom. If it is coming via front, you can see the lone pair present in the chlorine atom will repel the minus charge. So I can say what is the product that will be formed here is hydrogen here, another hydrogen here, another hydrogen here. Here there was chlorine atom was present, but this chlorine atom have not left until now. So how it will be moving out is when the C2H5O minus comes and attack this one. Okay, here I can say you will have C2H5O. When it comes and joins here, you can see the valency of carbon is now becoming 2, 4, 6, 8, 10. So we know that chlorine is an easily leaving group. So at this point, when it hits here, the same time this chlorine will leave out as Cl minus. It all happens in a single step. That's why we say it's a single step reaction. But you know, here the C2H5O minus is present on the back side. Okay, here I can say CH3O C2H5 is formed here. Okay, or the nucleophile comes from the back side. So what is happening? Suppose you have a compound like this. Now after attacking from the back side, you are getting an inversion is happening. Okay, is this clear for everyone? Whether the SN2 mechanism is clear? Hello?
Yes.
Okay, now we will see the stereochemistry of SN2 reaction. Then you will understand that as well. Stereochemistry of SN2 reaction. Okay, so I can say here you have a 1 degree alkyl halide is present. Now you are treating this with a strong nucleophile. Let me say it like Nu minus. Now you are also having DMF. Okay, so what will happen here? The Nu minus will attack from the back side and you will get NuR like this and Cl minus. Okay, so what is happened here? From the backside attack has happened. So other way we can say that after the reaction, inversion is happening to the compound because the nucleophile attacks from the backside. So such a type of inversion is called Walden inversion. Walden inversion. For example, one good example I can say, for example, if you are having a compound like this C, okay, here let me say one hydrogen is present. Here you have a deuterium is present, and here you have something like let me say some atom like tritium is present. Let me say I'm giving an example, and here chlorine is present. I know that this compound is chiral because all the four valencies are different. Okay, now when the nucleophile attacks this compound from the back side, let me say this configuration, if I am looking whether let it be R configuration. We know that chiral compound can be represented as either R configuration or S configuration. So suppose if it is R configuration. So when after the SN2 mechanism, what will happen? This will come from the backside and attack, and you will get a compound like NuCDT and hydrogen here. So the inversion, the configuration has changed. This will become S configuration. That is, inversion has happened. So please remember, after SN2 mechanism, there will be Walden inversion if the compound is chiral in nature. Okay. So this is the stereochemistry. But in SN1, you have seen that after the reaction, what is happening? Racemic mixture will be formed. But in SN2 mechanism, you can see the inversion of configuration will happen. Suppose here, if you have S configuration, then here what you will be obtaining will be R configuration, like that. Okay, so factors favoring SN2 mechanism also we have seen here. The nucleophile used should be strong and polar aprotic solvent needs to be used. Example here is acetone. Okay, and another example is DMF, dimethyl formamide. Is this clear for everyone? Any doubt with SN2 mechanism? Hello? And one more thing you can write here, rate determining step. Since it happens in one single step, I can say the substrate as well as the nucleophile is present in one single step. Here it will, since why strong nucleophile is used here, because this strong nucleophile will not wait for the chlorine to move out. So in this single step, both the nucleophile and alkyl halide is there. So I can say rate constant is equal to K into RCl, along with the concentration of nucleophile is also there. So I can say 1, 1, so its order is 2. So that means the SN2 reaction depends upon the concentration of alkyl halide as well as the concentration of nucleophile. But in SN1 mechanism, you can see that in the rate determining step, there is no nucleophile is present. So I can say in this case, the rate determining step is depending only upon the concentration of alkyl halide. It is independent of the concentration of nucleophile. This is another important point to remember. Okay. So in some exams, they may also ask like this: if the concentration of nucleophile is increased, which reaction will be favored? Then the answer is SN2, because nucleophilic concentration depends only on SN2 mechanism. Clear? Okay, so we have seen the first section of haloalkanes or chemical reactivity of alkyl halides, we told the first characteristic reaction of alkyl halide is nucleophilic substitution, correct? So nucleophilic substitution, and we have learned that this nucleophilic substitution happens in two main mechanisms, that is SN1 and there is SN2. Then there is another important characteristic reaction given by alkyl halide. This is the main one. In addition to that, alkyl halide will also give another important reaction. Can anybody tell that? Can anybody tell what is the other important reaction given by alkyl halide? Can anybody tell? You have 10 more minutes. So I can say the other important reaction is elimination reaction. Elimination reaction. So you can think of a shortcut like this. Whenever there is a polar bond is there, it can be between any element. If there is a polar bond means here X is electronegative, X is electronegative. So because of that, electrons will stay near to this one. So that means there is a delta plus here, delta minus is here. So in this case, there are two possibilities are there. This bond can be broken, correct? When this bond can be broken, then there will be a carbocation formation, okay? And halogen or something will leave like this, okay? Now this carbocation can achieve stability by two methods. For example, I am drawing a tertiary carbocation like this. This can achieve stability by two methods. One method is the nucleophile can come and attack here. So that's the reason this is what we have seen now. This is called a nucleophilic substitution. Other thing is you have learned hyperconjugation in +1. You can see here this carbon is getting positive charge. So the nearby carbons are this one, and this one. They are called alpha carbon. So what it will do is this alpha carbon will have alpha hydrogen atom. So the orbital of this hydrogen atom or the electron of this hydrogen atom overlaps with the vacant orbital of this carbon atom, and it will donate electron to this carbon atom. That is the other way it can become stable. For example, I can show that mechanism how it happens. Then you will understand whenever carbocation is there, there are two ways. One is substitution by a nucleophile, other method is elimination. Let's see that. So you have hydrogen like this is present. You have a central carbon. There is another carbon with the hydrogen atom present like this, and you have another carbon with the hydrogen atom present like this. So as I told, since there is positive charge is here, I can say the orbital, p orbital of this carbon, is vacant, So what it will do is the nearby carbon atoms, hydrogen atom, this will leave as H plus. It is not mandatory that this hydrogen atom should leave. Either this can go, 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 this can go. All are near to this one. So I can say there are totally 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 alpha hydrogen is stabilizing this carbocation through hyperconjugation mechanism. Okay, so one of them will leave as H plus. Then what this bond will do, this pair of electrons will do, this will see this vacancy in this orbital, it will shift it to here, and you will get CH2 here, then a double bond carbon, then there will be CH3 here, and there is another CH3. This will result in an alkene. Understood? So there are two major reactions given by alkyl halide. One is nucleophilic substitution and other is elimination. So we will see this in detail, how this elimination happens. Elimination can also be classified into two. I will come to that. Elimination can also be classified into two as E1 mechanism and E2 mechanism. We will see that in our next class. Okay. Is this clear for everyone until now what we have discussed?
Yes, sir. Yes, sir.
Okay. And one important point to remember here is heating is an important factor for elimination. Usually in E2 mechanism, heating is very much required. Okay. So we will come to that. Then most of the students will ask me a doubt, sir, there is SN1 can happen to alkyl halide, SN2 can happen to alkyl halide, E1 can happen to alkyl halide, or E2 can. So how we will distinguish whether for a particular alkyl halide, whether SN1 will happen or SN2 will happen or E1 will happen or E2 will happen. All these tips and tricks I will discuss in the next session of our video. There I will complete the elimination and we will do more questions for your understanding. Okay, so please listen to my video lectures also. There I am explaining all these things in detail. Please write down the notes, and also please listen to the question discussion shared to you. Listen to that, and if you have any doubt, feel free to ask in doubt clearance group. Okay, thank you.